Hello, QuantDev. This is Sharon Kim. I am a first-year student in the HDFS program working with Zita Orovitz. It is my great pleasure to introduce our speaker for today, Jonathan J. Park. He is a fourth-year student in the HDFS program, co-advised by Peter Molinar and Seaman Chow. He received his BA and MA in psychology with an emphasis in quantitative psychology from the California State University at Fullerton, with a focus on item response theory, test equating, and longitudinal SEM. Presently, he is actively researching discrete time dynamic network models, modeling directionality and non-directionality, clustering methods for intra-individual processes to identify nomothetic trends in idiographic processes. He also has a cool website if you're interested in learning more. So today, he will be presenting What the Fuzz, Leveraging Ambiguity in Dynamic Network Models.
Yeah, cool. Thanks. That was a really great introduction. It makes me sound a lot cooler than I actually am. Yeah, so my talk today is called What the Fuzz, and it'll be talking about how we can make use of ambiguity in community detection assignments. And kind of in the wake of Peter's Festdrift, a common theme in a lot of the discussions that were had was that Peter would talk about something, and then a couple decades later, we would realize like how relevant what he talked about was. And in the 4 years that I've been here in my individual meetings with Seaman, Peter, and also sometimes Zach, Peter has brought up his surprise that fuzzy community detection or fuzzy statistics haven't been applied more in our areas of work. And so this is kind of my attempt at making it a 5 to 6 year lag between him talking about it and it becoming a reality as opposed to a 20-year one. And basically, this talk is not super duper formal. This is more of a formalization of thoughts that I had during my comprehensive exams. So I had a question to talk about how we might use fuzzy community detection, both at the level of the dynamic networks as well as the level of like a person by person network. So how can we cluster people, but also how can we cluster the symptoms within people? And so this talk is really like a formalization of those thoughts that I had during comps. And if for anyone that's familiar with the comps process, it's a bunch of suppressed memories. So we'll see if this is like a set of cohesive thoughts as the talk goes on. So since time immemorial, I like to start my talks by listing the goals, the things that we'll probably get to, hopefully, as long as I remember the things that I rehearsed. And so what we're going to talk about, in not necessarily in order, but hopefully we'll get to each of these points, is I want to contextualize categories, how we use categories as they are now, but then also introduce the concept of fuzziness and how even in our modern era in our day-to-day lives, even when we use categories, they're inherently fuzzy, and some of those problems that come with not acknowledging the fuzziness in our categories. And then on top of that, I'll go into the foundations of fuzziness. Initially, I try to go with alliteration for each of these bullet points, and then I just gave up. So this is why it ends at foundations of fuzziness, but we'll talk about discrete community detection methods, as well as the fuzzy extensions of those. And then I'll briefly mention the fuzzifier, which is an actual term. And kind of interspersed throughout this talk, I'll mention places and examples where fuzzy community detection could be applied at the level of the variables. So you can imagine this is like a cross-sectional application, as well as the level of clustering, say like VAR models across multiple people. And from the get-go, I want to just give the answer, like the end point of the talk, which is that this is not a call to end the use of categories. I think categories and categorizations are useful heuristic tools, right? It's a way for me to get a lot of information really quickly. But what I think my point is that when we create categories or when we use categories, we frequently act as if there's these hard boundaries where the categories exist. And then whenever something that breaks that rule comes up, we make an exception, and we make exception after exception after exception until the boundaries become almost uninterpretable. So again, this isn't a call to end the use of categories. What it is a call for is to embrace fuzziness. So when we create categories from the get-go, maybe we should acknowledge that they're fuzzy to begin with, and that maybe fuzziness isn't inherently bad, that there might be information to be gained there in the fuzzy spaces. So let's give some context. I want to start really broad. I'm going to start with really broad statements, and then we're going to go into some examples, both in other fields as well as in kind of the areas that I care about. So humans love categories. I don't think this is like a controversial thing to say. People like categories, and they're a useful way of kind of condensing information. We can think of it similar to like a factor analysis or a PCA, where basically if I know that you're in a category, I might know other things about you. So if I know that you're a Democrat, I know probably who you voted for in the presidential election. And that is to say, there's also probably errors in that use of that category, is that I probably know who you voted for, but I don't know with 100% certainty who you voted for. And so I think categories, again, are useful, and also just like developmentally, a lot of children tend to exhibit dichotomous thinking. And hopefully as we grow into adulthood, we learn to see the shades of gray, though the past couple of years have taught me that maybe that's not always the case for a lot of people. But generally speaking, categories are a really useful way of describing kind of our reality. And I want to give everyone like a kick back to a really traumatizing time in their life, which is high school or maybe college, where we talked about, maybe you took an intro chem class or an intro physics class. And like physics for me has always been like a thing that I've really enjoyed. Before I switched my major to psychology as an undergrad, I wanted to study physics instead. But I switched for like personal reasons. And I'm sure all of us have at some point learned, if not about the specific types of polarities, we've certainly learned about different types of atomic bonds. And I promise you, if you think this is like complicated, the psychopathology example is a lot worse. So please bear with me. But like, I'm going to focus on the back end, right? So we can imagine that there are polar covalent bonds and ionic bonds. And we're taught that ionic bonds are the strongest type of atomic bond where there's a strong difference in the electronegativities. Basically, one atom really wants an electron, and the other atom could not care less if it kept its electron. And so the stronger the difference in the electronegativities, so here you can see it's delta E, the stronger the difference, the more likely it is to be an ionic bond. But we're taught this in our chemistry class or in our physics classes as if these are like discrete states, and they're not. So I did some reading. It was really fun to kind of go back, because community detection has a lot of applications in physics. So it's really nice to kind of see where these things are being drawn. So I have a couple sources of where the boundary is between a polar covalent bond and an ionic bond. So source A says that it's at a delta E of 1.8, which is fantastic, right? So if I have two atoms and their delta E is 1.9, I have an ionic bond. And then source B says greater than 2. So now my ionic bond is no longer an ionic bond, it's a polar covalent bond again. And then this paper that I read said, I don't know, it's between 1.5 and 2. It's somewhere there. And then the original person that developed the scale, this is called the Pauling scale, said it's 1.7, which is to say that there's this boundary somewhere between polar covalent bonding and ionic bonding, but that boundary is not clear. And to really drive home this point, source A and B are from the same book, but 4 chapters apart. So source A is chapter 4.3 and source B is chapter 8.2 in the exact same book. And they disagree on the boundary between where a polar covalent bond and an ionic bond begin and end, which is to say that the boundary is fuzzy, right? And this is a talk that I attended in the statistics department on modeling directional and functional maps for fMRI data by Dr. Zhang at the University of Pittsburgh. And one thing that she brought up, as well as in a talk that I gave at UCLA a couple weeks ago, is that ROIs, so regions of interest in fMRI data, also have relations across multiple networks. That is to say that a specific ROI doesn't necessarily belong to just one and only one network. It's probably involved in multiple networks. And so in that way, that particular ROI is fuzzy in its membership. It's not necessarily part of only one network or the other network. It belongs in multiple ones. And so now we get into the example for psychopathology. And for people that know me, I really like memes. I think memes are a really great way of conveying information or emotions and stuff. And so I'm a part of this Facebook group that posts scientific figures that look like memes, whether it's intentional or not. And so this is from a Swedish textbook on psychiatry talking about various psychopathologies. And I saw this on Monday and I was like, this is perfect. This is exactly what I need for my talk. And so here we see a bunch of psychopathologies or psychological disorders, and we see that they have a large degree of overlap. In fact, overlap is more common than it is uncommon. And it's a frequent criticism of the current ways in which we study and treat psychopathologies and psychological disorders. So recent calls, namely the high top comes to mind, is the hierarchical taxonomy of psychopathology, have called to acknowledge a more dimensional view of psychopathology and moving away from a taxonomic or I think it's called a Krapelian dichotomy. And these calls aren't new, right? So high top is from like the 2010s, but Kraepelin, where the Kraepelin dichotomy comes from, which is kind of the categorization of psychopathologies, Kraepelin himself in his later life in the 1920s wrote that it's almost impossible to deny that it's very difficult to come up with a firm diagnosis one way or another for various disorders. So he expressed regret essentially at coming up with kind of firm diagnostic boundaries that weren't actually that firm. And so a lot of these kind of areas are criticizing these unclear boundaries between the disorders, that there's not a clear decision point as to when you might have one disorder or another. And this is where I want to kind of inject that understanding how disorders are connected and where they share their overlap might not be a bad thing, right? So Jones et al. In 2021, but there's also a 2019 paper, used overlapping symptoms to identify what they call bridge symptoms, or basically symptoms that span the gap from one psychopathology to another, and talked about how those variables or those symptoms might be kind of the key symptoms to look at to prevent kind of a spillover or a cascade effect where one psychological disorder might kick off another one. And one of the problems in their paper was basically that the symptoms needed a priori assignment. So I have to know that the symptom belongs to a disorder for me to calculate certain measures. So I need to know that all the symptoms belong to depression, or all the symptoms need to belong to borderline personality disorder for me to come up with certain statistics. And so the argument, hopefully, as we move forward, will be that maybe there's a way that fuzzy community detection is a way of kind of capturing this nuance as well. So this is a super informal definition. I'm sure there's a much better one, but I'm going to go with this one, is that community detection is our, us seeking a way to find groups, clusters, communities, families, whatever you want to call them, that have more things in common with each other than they have with people outside of their group. So I should have more in common with my community than I have with people in some other community. And traditionally, in psychological applications and sociological applications, as well as just many other areas, we'll typically see applications of hard community detection. And that is to say that the decision points are usually your A or B. You can't have any nuance in that classification. And fuzzy clustering methods allow you to have some degree of membership across everything. And I'll talk about the specifics later. And kind of in line with these calls to acknowledge the fuzziness in psychopathology, various packages that cluster dynamics. So looking at dynamic network models, which is kind of my area. So like Gimme, graphical var, the alternating least squares var, and various other methods implement only hard clustering solutions. And it wouldn't be super difficult to add some functionality to allow for fuzziness. And so I'm going to talk about an example of community detection, and then I'll talk about how the changes might manifest in these packages. And one thing I want to note is that this idea of allowing fuzziness is not entirely different than spanning the gap in some of our work from ideographic to nomothetic. In a way, it's similar that we're spanning the gap instead from categorical to continuous data. So by fuzzifying our data, fuzzying the boundaries, we're kind of finding a little middle ground between continuous data and categories. So hopefully that makes sense. So I'm going to talk about these community detection methods just as k-means and the fuzzy version of it, which is fuzzy c-means. I don't think it's necessary to talk about more complicated versions of it because this is just to get the idea across. So k-means is kind of an algorithmic approach for identifying k communities, right? So users specify some k value. So I want 3 groups, and then n subjects are randomly assigned, or there's a principled way of doing it, but we'll just say it's random, randomly assigned to one of those k clusters. We calculate a mean, which is like the distance from each person to every other person. And then we shuffle subjects to clusters if the distance would be minimized by moving them to another community. And we repeat this again and again until we reach some convergence criteria. So in the case of k-means, we're seeking to minimize the subjective function, which really is just minimizing the within cluster sums of squares, right? So we're just basically taking the distance from every data point to its centroid. And the thing that I want to draw our attention to is that X here is only within S, right? So it's only for the subjects that are within that particular subgroup. So if I belong in subgroup A, I have no influence on the calculation of the centroid for subgroup B. And this will be relevant when I get to the fuzzy stuff. So let's talk about an illustration. These are simulated data that I made up, and I made them up because I obviously wanted a specific answer. So let's say you have 5 symptoms of depression, and then you have 5 symptoms of anxiety, and you have a bridge symptom here, right? So this is a good example of a bridge symptom. It's a symptom that will span the gap between depression and anxiety, where depression can only exert influence on anxiety through X. And let's say I want to find 2 communities. So I'm going to address what happens if you just say there's probably just 3 communities, but let's just assume that we fit a 2 community solution to this network. And because the assignment for k-means, it can be random, in some situations, X will be called a symptom of depression. And in other solutions, it'll be called a symptom of anxiety. And to address what happens if we fit a 3 cluster solution, we get 3 clusters where all of the depression symptoms belong together, all of the anxiety symptoms belong together, and then this is in a group all of its own. And so then the question is, obviously we can look at fit, but then it's a little weird. But we have to ask ourselves, is that a meaningful cluster to have one variable all by itself? Or is it more meaningful to kind of find a middle ground and acknowledge that I simulated these data, so I know that it belongs equally to both? And so can we acknowledge in some way that it belongs equally to both of those communities? And I'm glad that nobody asked that, but I asked that rhetorically so that I can progress the talk, is now we can talk about fuzzy communities. So this is the objective function for fuzzy c-means, which is, again, just the fuzzy version of k-means. And the thing that really is the most important to see is that we have this w value, right? So w sub I j to the m, where m is the fuzzifier. And as I said before, that is the actual scientific term for this thing. And it ranges anywhere between 1 and infinity. And I'll talk about what happens as we mess with the fuzzifier in another slide. And w is a matrix where the ith element of that matrix, or where the ijth element tells us subject i's, or the ith element of X and how much it belongs to the jth cluster, right? So how much does the ith value belong to the jth cluster across all of X? So then we have a matrix that is n by k. So how many groups we have by how many people. And we can calculate every cell of the partition matrix using this equation. And basically, it's just saying how much does one subject belong in cluster J relative to how much it belongs in every other cluster. And then we can see here that the fuzzifier exponentiates the denominator. So in the next couple of slides, I'm going to talk about what is the effect of the fuzzifier. So as I said, the fuzzifier can take on a value between 1 and infinity. It can't take on exactly 1 because then this doesn't work. So as m approaches 1, we have a hard clustering solution. It basically becomes equivalent to k-means. And so you have these discrete circles where even if a data point is here in the middle of this lighter blue circle, its value or its weight only affects the calculation of the mean for this lighter blue circle. When the fuzzifier takes on a value of 2, you can see that it adds some or increasing the alpha value. And so if a value is over here, it has some influence on the calculation of the darker blue circle as well as the lighter blue circle. And I use 2 as the example because this is the default in a lot of packages to use a fuzzifier of 2. And then as it approaches infinity, you can see that basically the borders of where these circles exist kind of ceases to be there, which is to say that every variable has an impact on the calculation of every centroid, essentially. So as you approach infinity, everything affects the calculation of every centroid, which is useless. So here's, again, going back to my simulated example, if we fit a fuzzy 2-group solution to this. And I want to note that based off of the certain fit measures, the 2-group solution in this case does fit better. So a fuzzy solution is better than a more discrete 3-group solution. So in this case, we have the 5 symptoms of depression, we have the 5 symptoms of anxiety, and then we have that weird kind of in-between symptom. And when we fit the 2-group solution, what we find is that there's kind of X becomes this variable that belongs equally to both, right? And I have this, basically this is from the simulated data, you can tell because it's called the QuantDev model. And so you can see that for every other variable, we have almost a 90, I'm interpreting this as a percent, technically they're not percentages, but they're close enough. They're all basically about 90%. Confident that they belong in one cluster or another. And then we can see that for variable 1, it's basically split half and half. So that is to say that we're unsure where this variable belongs. And again, this is my opinion. This is not a super formal talk. This is something that we still need to do work on. But it seems that this, at least to me, makes more sense to acknowledge that this is a symptom that has its legs in both depression and anxiety, as opposed to treating it as if it was a cluster all on its own. So here's like an illustration. So this is taken like straight out of my comprehensive exams. So this could be messy and there's some arbitrary decisions being made. So we had 50 subjects from a study on major depressive disorder. So we had basically half had major depressive disorder, the other half were pair-matched controls. And it's taken from this study from 2017. The subjects were measured 3 times a day, every day, at equidistant intervals for 30 days. So they had about 90 time points each, and they were assessed on 14 affect items. Basically, it's like, since the last time you took this, how do you feel? In the case of this, since I only want to look at kind of the symptom network, I basically took the within subjects means, and then I stacked everyone on top of each other, and I basically did a person network, I created a distance matrix of how far each person was from every other person. And then I searched that using fuzzy C means. I compared from a C of 1 to a C of 4, so 1 to 4 groups, and then C2 fit best in terms of partition entropy, the silhouette index, and the fuzzy silhouette index. And then here is an arbitrary assignment. I'm willing to talk about this if people have more principled ideas, but basically I said if the cluster assignment was less than 0.7, then I was going to call that ambiguous. And again, totally arbitrary and something that needs to be looked at further. So in this case, I'm only representing 2 of the dimensions, and this is because these are the 2 dimensions where the separation was the most clear, at least mostly clear. So these lighter blue people are the folks that had major depressive disorder, and then the red folks are the control group. And so we can see that the controls typically had higher happiness and lower depression. The depressed folks tended to have higher depression, lower happiness. This kind of makes sense. And then all but 2 of the black dots were folks who had major depressive disorder. And at the time that I was doing my comprehensive exams, the speculation that I had was that since all of the people with major depressive disorder were undergoing outpatient therapy, my hope was that they're moving in the direction of the folks who are in the controls. So the reason why they're not concretely classified as one or the other is because they are people with depression, but they're undergoing treatment and possibly they're responding to that treatment. Whether that's true, I don't know. We don't have that information in the data, but it is just speculative, and I thought it was interesting. So I've gone through a lot. I don't know if people have questions. I haven't been like looking. Okay, let me open the chat, and then I can at least have that open if people have things to say. Okay. So now I'm going to talk about how we can cluster subjects of people. So,
can I raise kind of a high level question here?
Yes.
So just to help people get their heads around things, how does a fuzzy community detection compare to the broad idea of like a mixture model?
I've had this conversation with Zach, and I'm not sure like what the equivalence would be, but I think they'd be really similar. Is that like the mixture model is also looking at kind of probability of you belonging in various classes. So then I would imagine it's similar. Because then you could also have people or groups of individuals that have an equal likelihood of being in either mixture class. So
okay. I mean I haven't dug too deep in here. It seems like it's going to be very close if you're building essentially Gaussian clusters, right? Sort of with Gaussian radius, a Gaussian radius, but that you could pick a different weighting scheme with a fuzzy cluster that might be more suited, right? If you're using something besides C-means and using DB scan or something that's density focused, you might be able to like sort of leverage that into a much more intricate mixture.
Yeah, after you mentioned it in that lab meeting that you had, I think you mentioned DB scan to Zach. I did some reading on it, and it also does have like fuzziness built into it. I think technically like fuzzy community detection was mainly developed to control for outliers, and so it's basically the same thing. And so I did read that DB scan has outlier control, so then I imagine it's also possible to do that.
Okay, I'm just trying to sort of fit this into where it fits with other types of analysis. So thank you, appreciate it.
Mm-hmm. Let me. Right. So now, is anyone? Okay, cool. So obviously, like these examples have focused on how we can cluster almost at the symptom level, right? So if we had just a bunch of symptoms of things, how can we cluster them? But something that we also do a lot here in particular is that we are clustering subjects based off of dynamics. So like I mentioned earlier, we have like GIME, graphical VAR, even dynamic mixture modeling. So this is really similar as Tim brought up. Alternating least squares VAR, and there's a ton of other methods that basically allow us to cluster people's dynamics over time. And so clustering with VAR happens, and also with its extensions or transformations. So structure VAR, graphical VAR are the ones that I've worked with. So those are the examples that I've added. And the argument that I have for this section is that incorporating fuzziness into the solutions could be useful for identifying people who exhibit dynamics that are kind of in between groups of people. So what that might mean, I'm not too sure. I think in my example, it's kind of drawing from this, even though this was on a cross-section of the data, is that if we have dynamics that are characteristic of depressives and dynamics that are characteristics of people with controls, then these folks might be exhibiting dynamics of recovery. Now, it's a little different because these folks weren't grouped together, right? So they're not in and of themselves a cohesive subgroup. So I don't know how we would model the fuzzy people, but this is, of course, something that we would just need to discuss and work on. So one thing I want to say is I made this figure during my first year, and I've used it in every single talk I've ever done. So I really want to give a pat on the back to first year Jonathan for making such a stand-up figure. So this is a standard VAR model. We can see that it's basically how variables at a given lag predict themselves and each other at the next time point. And so in this case, we have a var of order 1 or a var 1 because we're only going back one time step. Great. Here's the equation. You can assume that it's centered, which is why I don't have the mean vector. But basically, we have the vector of scores predicted by some phi matrix post-multiplied by your scores at the previous time point, plus some residuals that are normally distributed with the covariance matrix of psi. Relevant for our discussion is just, I can't highlight this. That's stupid. Relevant for our discussion is the phi matrix, which is the matrix of basically the dynamics, what is happening as you are going over time. And so when we cluster var models, generally we're going to use the phi matrix because that contains like the dynamics that are occurring. And then with graphical var, so if you're familiar with Gimme, we use the A matrix as well, which is the matrix of contemporaneous effects. Some subscripts would have it as phi 0. And then with the graphical var, we would also use the precision matrix. Technically, you could use the covariance matrix when you're clustering var models too, but I don't see that being done. So with the graphical var, we would use the inverse of the residual covariance matrix. And so basically what we would have when we're clustering a var model is we would have a phi matrix for each person, right? So let's go back here. So each person has this model. And so then they all have 4 potential effects, phi 1, 1, phi 2, 2, and then the cross regressions. And what we can do is we can create an adjacency matrix. I'm calling it omega. Usually we call it A, but I already used it, so I'm calling it omega. And so omega sub ij tells us the number of common dynamics that the ith and the jth subject have in common. So if we have this as our var model, then what we would find is basically, I have this autoregressive effect from variable 1 at time -1 to time, and maybe Tim doesn't have that. So then we wouldn't have that path in common, and it doesn't go into account. So in this model, the most things that we can have in common is 4, and then the least is 0. We can have nothing in common, or we can have up to 4 parameters in common. So then each cell is populated, and generally, when I say common, our definition is usually polarity and non-zero status. So are we the same in the sign? Is my autoregression positive, and is your autoregression positive, or is it negative? And then also, is it non-zero? So that's generally how we'll do clustering. This is kind of applicable across almost all of these different ways of clustering var models in some way, with nuance. There's obviously differences across them, but generally this is kind of what the solution tends to be. And so this is an example. This is actually the simulated emotion network that I made up, but you can see that within the 2 rectangles, we can see that subject 2 and subject 3 have 10 things in common. Whatever, I don't know what the max is because I made this up, but they have 10 things in common. But subject 2 and subject 7, I guess technically it's row, then column. So subject 7 and subject 2 have nothing in common. And then within the rectangle, you see that subject 7 and subject 8 have 10 things in common, but then, so you basically have this diagonal or this off diagonal that is completely empty because they have nothing in common with each other. And then everyone within the communities has a lot of things in common, which is basically the spirit of community detection in some way, shape, or form. And so I've basically, what I did, and so this is highly speculative territory here. But what I did was I fitted graphical var models to the whole sample of the depression study that I mentioned earlier, and then I just extracted a similarity matrix or the adjacency matrix, and I searched it. I tried to find a subgroup solution, and a 2-group solution also fit well in this group relative to a 3 and a 4 group solution. And there's not a whole lot of information that I have at this time. I don't really have like a conclusive thing, but I have trends. So typically, the people with major depressive disorder tend to be concentrated towards the middle, and then they radiate outwards, whereas the controls seem to be evenly distributed throughout all of the 3 clusters, or the 2 clusters in the fuzzy space, I should say. And then within these 3-ish, kind of 2.5 groups, I guess, the mean levels of depression were the highest for the depressive folks within the fuzzy space. followed by the depressed folks within the red cluster. So fuzzy people tend to have higher mean level depression and also lower mean level happiness, which were just two of the variables that I looked at, relative to people in the outer or the inner categories. Which, again, I'm not too sure what this could mean, but potentially it could mean that there's something about the fuzzy people who are exhibiting these dynamics that's worth further study if they're exhibiting higher than average depression and lower than average happiness. And that's basically just reiterating what I said here. So this is other thingies. So this is kind of like a recap and like other issues that exist. So basically various developmental, psychological, and a ton of phenomena in the natural world are fuzzy, and we just kind of don't acknowledge that sometimes. And again, as I said at the top of the talk, the goal is not getting rid of categories, but that we should just say that they're fuzzy and acknowledge the fuzziness that is inherent to these categories. And that the lack of acknowledgement can lead to some confusion and can obscure the fact that that's a place where we should be directing more like attention to, whether it's to refine those boundaries or to kind of get a better understanding of when the fuzziness occurs. So fuzzy community detection just allows us to quantify degrees of membership. As Tim noted, it is kind of similar to mixture modeling. Ambiguous data points and hard algorithms end up being forced into one of the two communities, or we have to enumerate another group just for that one data point or for those few data points. And that's even if the fit is relatively poor. So as I said with the k-means example, the 2-group solution fit technically better than the 3-group solution, but it didn't make as much sense. And it masked the fact that that thing belonged equally to both as opposed to just one. So the sums of squares explodes for one subgroup because it has to incorporate someone that's further away. And then applications of fuzziness can reveal basically ambiguous data points. And in some applications, like if we're studying psychological networks or symptom networks, those ambiguous symptoms might be useful as being classified as bridge symptoms because they have that equal belongingness across the two groups. Some things to consider. So I just wanted to have this like formalized because I've mentioned this to several people, but I've never been able to write this down anywhere. I think, Mike, I mentioned this to you at lunch, is that the clustering of VAR models by path counts can be improved because the way that we do it is we treat these as if they're unipartite graphs. So if people don't know, a unipartite graph is just a network where there's one type of node. So if we want to think about this as an authorship network, we have a bunch of authors that are connected to each other, and the edges represent, did they publish a paper together? But in reality, this is actually a bipartite problem. It's where we have two types of nodes. We have people, and then we also have parameters. And you can cast a bipartite network as a unipartite network with weighted edges, but you lose some of the information, which is to say you lose the fact that with the bipartite graph, I know that subjects 1 and 2 share all of their autoregressions in common. When I recast that as a unipartite graph, I know that subjects 1 and 2 have 10 things in common, but I don't know the specific parameters. And the thing that changes is the form of modularity. So basically we have an objective function that we try to maximize with community detection or some community detection algorithms. And that definition of modularity will change if we're looking or searching a bipartite graph. Now, these programs and functions seem to do relatively well at finding groups. So it's not that it's like problematic, but maybe it could be better. And it's certainly something that I would want to explore a little further on down the line. Some work has been done on differentiating clusters based off of different metrics. So there's a paper that I was sent a little bit ago that talks about how maybe, particularly with emotion dynamics, the dynamics don't differ that much between the clinical and the non-clinical populations. But what does differ is the effect sizes of those effects. So basically, we'll have a denser network, and density is like how strong are the lagged effects, how strong are the cross regressions. And so there's some work being done that shows that the overall density, which is just the sum of the autoregression coefficients, tends to be higher in folks with depression relative to controls. And so if we try to differentiate this based off of the transition matrices, we don't have the sensitivity to do that, because we look at, is it non-zero? Is it positive? Is it the same sign? And so we don't necessarily pick up on that nuance. So community detection on the sizes of the effects or the densities might be another way of kind of parsing out these differences. And I made this comment earlier, but deciding on the appropriate number of communities is hard. We have to enumerate across values of K or do K-folds cross-validation or something. We have to find a way to pick the correct number of groups. And there's more sophisticated algorithms that can do that. So there's a fuzzy extension to walktrap that I've been reading about that technically you don't need to specify K. It'll just find it based off of some optimization value. But also the cutoff. So how we determine what is ambiguous will differ. So as I said, for my comps, I used a cutoff of 0.7 or less, but that was out of comps desperation, and I have no reason to stand by that value. So that's something that could also be optimized in the future. And yeah, so that's basically my talk. I think that's basically everything. I don't know if people have questions or comments or things. I see that Tim has a question.
I know you're shocked by that. So you said at the beginning that your goal was not to throw out clustering as an approach, and I guess one of my questions is, why not throw out clustering as an approach entirely? If you're at a point where you're already doing fuzzy clustering and you've already got distances, you could throw something like multidimensional scaling at it and come up with latent factors, like latent scales that let you map these things onto a continuous space. Actually, Zach and I have been talking about some other possibilities using a method called deep walk that I'd love to talk to you about, but probably not in this conversation. But like, why not just move to a continuous space? If you're saying clusters are too rigid and there's no reason to draw arbitrary lines, why not just stop drawing arbitrary lines?
I think I mentioned this in my like panicked spring break email that I sent you. But I think like the benefit to the, yeah, right. So I kind of alluded to this when we were talking about, I mentioned briefly like the idiothetic, nomothetic thing and finding like spanning the gap. So I think that in some cases, categories are still useful and still have utility. So I think it's a matter of finding situations in which a purely dimensional approach is relevant or more relevant than acknowledging that there's some similarities. So using this as the atomic example is that technically there's no point at which a polar covalent bond becomes an ionic bond, but it's useful in terms of having expectations for reactivity and how difficult it is to break those bonds, to know that generally this bond is ionic, so it's going to be difficult to break those two atoms apart. So I think it's a matter of topic by topic where it's going to be, and I don't have like a clear answer, but I think at least in my honey nut filios, I think that there's something to maintaining some form of boundary, even if we loosen those bounds. But I'm totally for like anywhere in that space. I think we need to span the gap and do research across the whole spectrum, which is ironic because it's about clustering.
Thanks.
Thank you. And then Mike, I see you have a hand up.
So keeping a little bit with the physics chemistry theme here, the paper in physics by Erwin Schrödinger that talks about Schrödinger's cat has an example in there that I think about more than the Schrödinger's cat example, which he distinguishes, but he wants to draw a distinction between a clear picture of fog and a blurry picture of just the environment. So it's trying to get at, really it's getting at the nature of reality. Is there really something fuzzy about how people are clustered, or is our view of the separation kind of error prone? So is this sort of, are we getting at something in the nature of reality when we're doing this sort of fuzzy clustering, or are we just sort of accounting for like measurement error, or like, I don't know, someone had a bad day, or like things like that. So like, in your view, what are we trying to capture, or the distinctions that you could capture with fuzzy clustering or these kind of fuzzy community detection methods?
Right. So so I mentioned earlier the origins of like fuzzy community detection is the control for outliers. So like in a way, this whole talk is kind of a bastardization of the original intent, which is just these are noisy data points and we should get rid of them. Mm-hmm. But then I think when I was doing my comps, I read one paper in Psych that does use fuzzy community detection, and their proposal was basically in line with this, was that yes, they're outliers in reference to like the centroids, but that doesn't necessarily mean that they're meaningless. And so again, I think it ends up coming down to the context that we're studying these things or these processes. But because I can simulate an example in here where there is a meaningful or a conclusive outlier as well. And so in this case, I simulated it to be a meaningful thing that exists between and is equally connected to both. But so I think it's also on like the variable level. So when I look at this variable and I look at the data and the conclusion, I can draw that this is probably a bridge symptom, but there's equal likelihood that there's another symptom over here that has ambiguous membership, but it also sucks in terms of its fit to either category. So then I think it's data dependent, and where we would draw those lines, I'm not sure. I don't think this is all new. This is from comps.
Another, if I can just monopolize the discussion a little, another thing that sort of makes me think about is the qualitative theory of dynamical systems, or bifurcation theory. So there are the idea that there are points where there's a qualitative shift in how a process works. Like somewhere in the parameter space, if you change just a little bit from one side of a boundary to another side, you get some very different behavior. You get different fixed points, fixed stable things become unstable. The world turns upside down. Like these things kind of happen. It's different from sensitive dependence on initial conditions. But I wonder if there's something to be said for that kind of qualitative theory here. We're trying to get at the nature of quantitative versus qualitative differences, which we're not about to solve. But I wonder if there are further elements of kind of known theory that help.
I have no answer. Yeah, I'm not quite sure how. At least I'm not familiar. Yeah, I don't know.
So like here, for example, like that, like just with this k-means, like it's not even a dynamical system, but like if X just dropped out of the graph entirely, you have a totally different graph structure.
Yeah.
With it versus without it. Whereas if you had a lot of connections, between the anxiety group and the depression group, dropping one of those connections that links kind of one subgraph to the other subgraph doesn't change the network all that much, doesn't change the connectivity all that much. So I wonder about, small changes are kind of critical features of graphs that change.
Yeah, like the resilience.
Yeah.
Yeah. So in this example, yeah, if we removed X, it would have a huge impact on the network. And actually, I'm taking a network class in the physics department, and I think like on Monday we literally just talked about resilience.
Yeah.
To like cascading. I think it's called like the lecture is called Resilience to Cascading Failures.
Yeah.
Which is like a great name. But that, yeah. So we can model kind of how the network would change given like perturbations and also like edge or node removal. Mm-hmm. And this kind of relates to like a talk or like a discussion I had with someone where another thing that could be looked at is how these connectivity maps change over time.
Yeah.
So then in terms of looking at, so let's assume we're looking at either the fuzzy, I'm going to choose the fuzzy example because I think that might be relevant. So in the fuzzy example, it could be the case that even within an individual, this is only a temporary stop until the X node, this ambiguous node, ends up picking or choosing to be, more conclusively about depression or more conclusively about anxiety. So I think so it can flip its association over time. And then, I guess if we're talking about this in terms of symptoms, I don't think the symptom would like drop out per se, but then its value and its weight can change such that it becomes more relevant to one psychopathology rather than the other. I don't know if that's even related to what you asked, but that's my tangent.
Okay, it was my tangent
I think
too.
so. I like some of this line of thinking of like what happens if that node isn't there, right? Where you've got this sort of hybrid node. But if this is like a partial correlation network, right? If that node isn't there, then all of the links that go through it pop up as weaker links, right? And now you have a bunch of things that are at the fuzzy border between your two clusters instead of just one thing that's at the border. But I think that's a really important point when you're talking about these kinds of networks, is like inclusion of one or two nodes can suddenly separate things more or draw them together more, right? Just depending on how the links through those happen to work out. It really it leads to some very interesting questions about stability that I think are really worth investigating, that I don't know anybody really looks too closely at for the most part. I mean, like betweenness centrality gets at some of that, but only lightly.
Yeah, there's a couple papers. There's like a back and forth between like Aidan Wright and Denny Borsboom on replicability of partial correlation networks that happened a couple years ago, or maybe a year ago. I'm not sure, but yeah, I don't think that produced anything like conclusive, but it was a fun like series of papers to read.
Some of our attempts to use partial correlation networks have found similar things, that stability was just not a strong suit of those kinds of networks. Although it sounds like there are some ways to get around that. I actually have a different question, and I don't know if you addressed this already, but I come up against this every time I try and do clustering. What if you ran this clustering analysis and all of the nodes on the left side showed up in one cluster and all of the nodes on the right side showed up in the other cluster, and you've got fuzzy ones in the middle, and the clusters that you got just don't look anything like the theory that you're starting from? This is something that happens a lot of the time in clustering, right? It might be the case that there's external factors that are leading to stronger clustering than the ones that you're finding. Like, how would you interpret that? What would you do with that?
I would give up. I know that I don't know if I'm allowed to bring Zach into this conversation against his will, but I know that I've spoken with Zach about some solutions from Gimme. In particular, I think like in one of the empirical applications for a paper that we've been working on, we were looking at, how well could we find subgroups related to the true like diagnosis, and it failed terribly. Like it almost never matches up with the diagnosis. And then I brought this up to Zach, and he was like, "Yeah, you will never find like a solution where the subgroup matches with like the clinical diagnosis or like the formal diagnosis." So I think at least when I've done this, I almost at this point never have an expectation that it will align with like say a diagnosis or like a theory. And I'm more excited when it does. But yeah, I think you mentioned this in our email about like, if there's like confounding covariates that could exist. And I'm not sure how we would account for that in the network beyond like stratifying it before doing the community detection.
I mean, or, depending on what approach you're using some kind of priors maybe. But I kind of wonder if it might not be worth at least using an intermediate representation that's spatial, Because we know with a spatial analysis, we could build a discriminant function or something like that to find our clusters. And probably there are fuzzy discriminant functions we could apply that might do something similar. I just wonder if there's an opportunity there to be able to sort of force a rotation on things that might be more sensible for whatever you're interested in. I know I saw Mike Hunter was going to say something early on in this.
Zach's here. So
oh, okay.
Did you
Zach,
want to say
thoughts?
something, Zach?
Yeah, I could just add that, like, you know, what Tim said is, at least in my experience, like 100% right. That, you know, it never seems to like cluster on features that you think you're clustering on. So, you know, in terms of like trying to replicate something like a diagnostic category, like I've never seen anything come even close, at least in terms of these like dynamic network stuff. So yeah, like what happened with Gimme, for example, is like people pretty much just started using like the confirmatory subgroup options where you just specify the clusters in advance and then the algorithm operates from that point. So yeah, I think like that those intermediary type options make the analysis a lot more useful.
And I also want to add that it could also be that we're clustering on the wrong things. So like I noted, is that a lot of the work that's coming out now is on the density of the networks, and none of these approaches look at density at all. So then it could be that, you know, there's some, like, particularly with like an affect network, where we might not see necessarily a huge difference in the structure of the network as opposed to the weights of the network. And so in those cases, it might just be that we're also clustering on, like, there's a limited amount of variability in the network structure to begin with, and then we're capitalizing on like one or two differences across people across the whole networks, and then we're trying to find like a meaningful difference, when it could be that maybe it's just, if we looked at densities, people just have much stronger connectivity even if they have the same network structure.
So a classic result, a classic disappointing result in mixture modeling and a lot of cluster analysis is you find three clusters, broadly thought of as low, medium, and hot.
Yep.
Or mild, medium, and spicy. You know, like essentially, it's a cluster solution that looks like, well, there's just something continuous there. Does the fuzzy methods help you get away from that? Does it make it worse? Are there parameters in there that would let you know that you're clustering something that doesn't really belong in clusters?
So there's like some fit measures. I mentioned like the partition entropy and the fuzzy silhouette index that give some idea of whether you're being excessive in the enumeration. But I haven't like looked super into how each of them work. I just know
excessive
like,
versus a one cluster solution of like there could be a continuous variation that matters, as that the cluster algorithm will pick up and chop into bits.
Hey, like, I kind of want a continuous stably dense space is like the pathological example for a clustering solution, because then it's just like dropping lines anywhere and they're just all as good as each other.
Yeah.
Right.
Yeah, and I don't have like a clear answer for that. But then in contrasting it with the hard clustering, you're going to be forced to have, you're basically cutting off the whole, you're basically like having no gradient at all between any of the clusters that you enumerate. At the very least, the fuzzy solutions will acknowledge that there's ambiguities, even if it's in the arbitrary distribution that you're cutting up.
Well, like with k-means, there's like a within versus between sums of squares metric that's usually looked at that tries to tell you if there really are clusters, like at all.
Yeah, there at least in the package that I used for these analyses, we do also get that.
Okay.
So, but then like I think the definition again is also fuzzy because technically everything has a weight on every centroid, but it's just limited by the fuzzifier. Does anyone else have questions? I think I said at the end that you can send other comments and things to my email.
There's a question in the chat about what packages you're using.
For these, thank you, Tim. Package for fuzzy communities, I use ppclust, fclust also works, and then you can just use igraph for hard community detection. igraph does not have a whole lot for fuzzy stuff. I think there's like one option, but then its fuzzy solution forces the uncertain nodes to be explicitly labeled as both. And so it's a little different than like a purely fuzzy solution. Yeah, it should be called ppclust. Oh yeah, it's ppclust. Yeah, my bad.
PPL cust.
Yeah, not that. Don't install that package. I don't know what that does.
Okay.
Right.
Well, thanks very much, Jonathan.
Thank you, folks.